let's jump right in. Today, we're exploring one of the most fascinating mathematical tricks in all of solid-state physics, effective mass. We're going to unpack a concept that literally makes our modern digital world possible, all by completely bending the rules of what we think we know about physical reality. So get ready to challenge some of your core assumptions. Think about it for a second. Is the mass of an electron actually constant? If you've taken a basic physics or chemistry class, you probably memorized the rest mass of an electron as this fundamental, unchanging constant of nature. It's roughly 9.11 times 10 to the negative 31st kilograms. Fixed, right? Well, today we're going to completely upend that idea. We're going to see how, inside the materials powering the exact device you're using right now, an electron's mass is anything but constant.
Here's how we're going to break it down today. First, the mass illusion. Then, curvature and crystal momentum. Third, the negative mass mystery. Fourth, beyond the perfect parabola. And finally, real-world tech applications.
All right, Section 1, the mass illusion, and how we start breaking the rules of classical physics.
Picture a free electron moving through a perfect vacuum. In that totally empty space, it behaves exactly how Sir Isaac Newton would tell you it should. Apply an electric field, and it accelerates based on standard classical mechanics. Good old force equals mass times acceleration. Its mass is that fundamental constant we just talked about. But drop that exact same electron inside a crystal lattice, like a block of silicon, and everything just goes out the window. Suddenly, this electron is trying to navigate a dense, periodic obstacle course of atoms and interacting potential energies. Quantum mechanics totally takes over. Instead of acting like a simple particle, it behaves as a wave packet moving with a specific group velocity. We literally can't use standard Newtonian physics anymore because the lattice is just constantly pushing and pulling on our electron.
So we have a problem, right? We need a workaround. Because honestly, rather than solving impossibly complex Schrödinger equations for every single microscopic interaction as the electron bumps its way through the crystal, physicists came up with a brilliant shortcut. They called it effective mass. It's essentially this mathematical contraption that takes all those chaotic, complex forces from the lattice and bakes them down into a single, modified mass parameter. By swapping in this fake mass, we can actually go back to using our simple classical equations. We just treat the electron as if it were a free particle again. It's an absolute lifesaver of an illusion that saves engineers an enormous amount of mathematical headache.
Okay, moving to Section 2, curvature and crystal momentum. Let's actually visualize this math. The shape of the energy band directly dictates how our particle is going to move. If you look at this EK diagram, which maps energy against crystal momentum, or the wave vector k, pay attention to the peaks and valleys. Those are the band edges where all the important semiconductor action is actually happening. Up top, that red curve has a very sharp, steep curvature. Down at the bottom, the blue curve is much wider and flatter. Now, in this mathematical framework, a steep curve means a small effective mass. The electron accelerates incredibly fast, like it's practically weightless. On the flip side, a flat, weak curvature means a large effective mass, making the particle super sluggish and slow to respond.
And here is the simple formula that translates those energy curves directly into the inertia of the particle. Effective mass is inversely proportional to the second derivative of the energy with respect to momentum. Now, if you remember your calculus, the second derivative is quite literally the curvature. So, because of that inverse relationship, high curvature means low mass and low curvature means high mass. It perfectly packages that whole complex quantum crystal environment into one neat, workable number.
Which brings us to Section 3, the negative mass mystery, and what happens when Bragg reflection takes over.
This is where things get truly wild. Imagine an electric field accelerating our electron through the crystal. It speeds up, moving higher and higher on that energy curve we just looked at. But as it accelerates, its associated quantum wave starts interacting really heavily with the periodic atoms of the lattice. Eventually, it hits a specific spot, the inflection point on our curve, and the wave actually begins to bounce back. This is what we call Bragg reflection. Right at this exact inflection point, the backward momentum from the reflection perfectly cancels out the forward momentum from the electric field, so the electron just stops accelerating forward. It doesn't matter how hard you push it. Mathematically speaking, its effective mass has just become infinite. But wait, it gets crazier. If you keep pushing past that point, the Bragg reflection actually overtakes the forward motion. The crystal pushes back so hard that the electron accelerates in the opposite direction of the electric field. It's moving completely backwards. And mathematically, we describe this by saying the electron now has a negative effective mass. It feels totally counterintuitive, but it's a very real phenomenon dictating how these particles behave.
Let's look at section 4, beyond the perfect parabola. Because, as you well know, real life is rarely a perfect curve.
This graph brilliantly illustrates why real-world applications need a slightly more complex model. See, when electrons start filling up the bands and moving away from that absolute minimum edge, the curve flattens out. This is a phenomenon known as the Kane quasi-linear dispersion, and because it's no longer a perfect parabola, a single curvature number just won't cut it anymore. Depending on exactly what you're measuring, you literally get different masses. You've got the curvature effective mass for your basic acceleration, the transport effective mass when you're looking at gradients, and an optical effective mass that takes an average across all occupied states. The mass literally changes depending on the lens you use to observe it.
And this non-parabolic reality leads to what we call band-filling effects. When a device heats up, or when we pump a material full of charge carriers, like when we dope a semiconductor or blast a solar cell with intense sunlight, we shift the Fermi level. We are physically forcing electrons higher up the energy band into those flattened non-parabolic regions. And as they get pushed up, their effective mass fundamentally changes. It actually increases. So our simple little shortcut breaks down here, and we have to use much more rigorous calculations to understand how the device is going to hold up under a heavy load.
Finally, section 5, real-world tech applications. Let's look at why all this math actually matters for the devices in our pockets.
When we compare the effective masses of electrons and holes across different semiconductors, some really fascinating patterns emerge. Take a look at gallium arsenide at the bottom there. Its electron effective mass is incredibly tiny, just 0.067 times the rest mass of a free electron. Because it's so extraordinarily light, electrons can just whip through it at blistering speeds. This low effective mass is literally the fundamental reason we use gallium arsenide over silicon for high bandwidth applications, like your cell phone. And then check out germanium right in the middle. It has this extraordinarily small hole mass of just 0.04. That means the positive charge carriers in germanium can respond almost instantly to rapidly changing high-frequency electrical fields without lagging or acting sluggish. And because of that tiny effective inertia, germanium is actually making a massive comeback in modern high-frequency electronics.
But we definitely still have to account for those non-parabolic band-filling effects we were just talking about. For example, in advanced perovskite solar cells, specifically MAPI, as the electron concentration increases, the bands flatten out so much that pumping them full of electrons literally doubles their optical effective mass. And the result of that is pretty catastrophic. As the concentration hits 10 to the 19th per cubic centimeter, the electron mobility just absolutely plummets. They get heavy, they get sluggish, and mobility drops by a factor of 3. If engineers don't account for this changing effective mass illusion, they're going to completely miscalculate the efficiency of tomorrow's solar panels.
So we've seen how the mass of an electron, something we normally consider a hard fundamental constant, is, at least inside our technology, just a highly useful mathematical illusion created by its environment. So I want to leave you with this somewhat provocative thought. If the mass of the universe's basic building blocks is really just a matter of perspective, what else about our physical world is just an effective illusion? Keep questioning, keep learning, and thank you so much for joining me for this explainer.